Okay, so last week we defined the modular congruence between integers. So two integers a and b are said to be congruent modulo m if a minus b is a multiple of m. So and a and b are a is congruent to b modulo m if and only if there exists an integer k such that a is written as a b plus k times m. And we also defined what's called the congruent classes of a modulo m. So for example, if m is an integer 3, there are 3 congruent classes denoted by 0 bar, 1 bar, and 2 bar. So there are 3 classes, and the 0 is the set of integers such that a is congruent to 0 modulo 3, and the same applies to 1 and 2. So you can easily observe that every integer belongs to exactly one of these congruence classes. In other words, the set of integers can be represented as a disjoint union of these 3 classes. So disjoint union means that the union of this set is a set of integers and there's no intersection between these 3 subsets. We can also define the sum and product of integers modulo m. We call it arithmetic operation modulo m. So here's a very useful theorem. So suppose that m is a positive integer and there's integers a, b, c, d such that a and c are congruent to b and d modulo m respectively. Then we can show that a plus c and a times c are congruent to b plus d and b times d modulo m respectively. So for example, 7 and 2 are congruent modulo 5 and 11 and 1 are congruent to congruent modulo 5, then the summation of 7 and 11 is 18, which is congruent to 3 modulo 5, that is 2 plus 1. And the same is hold for this multiplication. Proof is very easy. We will just use this theorem we already have seen in this slide. So from the conditions this and this, we have that there exist integers s and t satisfying these 2 equations, and then you just you can check the facts that b plus d and b times d are represented as the sum of a plus c and a multiple of m, or a times c plus a multiple of m. So that we conclude that a plus c and a times c are congruent to b plus d and b times d modulo m. So as a corollary, we just we can also just apply the previous theorem to obtain the following statements: that a plus b modulo m is equal to a modulo m plus b modulo m modulo m. So recall that we use the same modem notation for 2 different types of relation and function. So first, if we use this notation, it means that a and b are a is congruent to b modulo m. But when we use some notation like a mod m, this is not, so this is a specific example of a relation, I said. But if when we use this notation, this is not a relation, but this is a function. So a is an input of function, and we take a modulo m. so that output is another integer. So that's why we use this equivalence symbol here. While we use equality symbol here. So this is a relation over integers modulo m, while the second equation is just equality over the set of integers. So a modulo, this mod m is a function from z to 0 to n minus 1. So now you can, when you understand this corollary, this is in addition between integers, but this is a modulo n function. So this result is an integer between 0 and n. So this result is an element contained in this set of integers from 0 to n minus 1, and the same applies to the right hand side. And you can just to prove this corollary, you can simply apply the previous theorem to this corollary. You can easily obtain the fact that left hand side and right hand side are concurrent modulo m first, and both sides are contained in this set of integers from 0 to n minus 1. So they should be equal as integers. So now we finally define this set of integers from 0 to n minus 1, and this is denoted by g sub m. So previously we defined this set 0 bar and 1 bar, something like this. So this was in modulo m space. This is a set of integers which is congruent to 0 modulo m. So now we don't have this bar notation here, but the intuition behind this notation is that this 0 is actually correspond to this 0 bar congruence class. So meaning that this m integers from this m integers 0, 1 to n minus 1, or I would say some representative elements of this m congruence classes. So meaning that we just pick one element from this and set this as a representative of this set, and the same applies to 1 bar. So there are many elements here, and I just chose this element as a representative of this congruence class. So since we had m different congruence classes, we have this n representative of these classes. So we collect them and we define this set g of m as a set of these representative integers. So, and now this is of course an integer, but you don't need to consider them as integers, but you can just identify these integers as with these congruence classes. So we are writing integer, but you're actually working on these congruent classes. Because in the world of modulo m space, this 0 and m are no longer different elements. So they are different over the different integers, but they are equivalent in modulo m space. So you just no longer distinguish this 0 and m. They are just the same element in this GM space. So here I'm writing, so in many textbooks, we define this GM as a set of integers between 0 and n minus 1. But if you want, you can come up with your own definition. So for example, You could use m instead of 0. That's totally fine. Or you could use sometimes for some efficiency reason, we use this signed version of GM representation. Like we can sometimes pick these representative elements from the set of integers between half of m and minus half of m, so that the size of absolute value of these values can be minimized. So any selection is fine, but of course this is not acceptable. Like if you use something like 0, 1, 4, this is not acceptable because of this 1 and 4 are equivalent to modulo 3. So this is not okay. But for example, this is okay because 0 to 7 is actually the same as 0 to 1 because 7 is equivalent to 1 modulo 3. So yeah, so that's the definition of GM. And we define this addition and multiplication operation over this GM set defined by like this. So, but we are gonna stick to this definition just for now, just to avoid confusion. So this mod m returns integer. So now we can say this mod m is a function from z to gm. For given a, we obtain a mod m, which is an element of this set. And between these elements of gm, we will define these arithmetic operations, addition modulo m and multiplication modulo m like this. So for example, 7 plus 9 modulo 11 is defined by literally 7 plus 9 modulo 9, modulo 11, which is 5. This is another element in Z11. And so same applies to the multiplication or negation operation. And when it's very clear from the context, then we can just remove this m here and simply write plus m. We simply use this plus m dot notation for the simplicity. And this arithmetic operation modulo m have good properties. Like, of course, this set of this gm is closed under this addition and multiplication modulo m. So if you add two elements of gm and take modulo m, that's going to be definitely another element in gm. And it also satisfies associativity law and commutativity law with respect to addition. And there exists identity elements with respect to addition and multiplication. So identity elements for addition is 0, of course, and identity elements for multiplication is 1. And there is a element inverse of addition. So in the set of integers for given a, minus a is a inverse element with respect to addition because their sum is an identity element 0 for addition. But in the world of in this modular space, minus a. So if a is some integer in this set, then this minus a may not be an element of GM because it's a negative integer. So if we add m here, then now this belongs to GM as well. And m minus a is also congruent to m modulo m, minus a modulo m. So in the set of this modular space, modular integers, m minus a is actually the same as minus A. So we can say n minus A is additive inverse of A. And it also satisfies distributive law. You can easily prove these properties. Sorry, I missed some questions. Third one in example. So, Hyogon, do you mean this one? I think this is a correct example. Yeah, negation of 7 is equal to 4 because 7 minus 7 and 4 are equivalent modulo 11, and this 4 is an element of this 11. And in abstract algebra, we call a set with these two operations, addition and multiplication, a ring. If this ring satisfies like these conditions, so the set of integers or set of rational numbers or set of real numbers or set of complex numbers, they are all different rings. But this GM is another example of a ring in abstract algebra. Okay, so before we go to the next chapter, we just stop here and look at briefly about integer representation. So in practice, we mostly use this decimal representation, like 351 is actually means that 3 times 10 squared and 5 times 10 to the 1 and plus 1. So we use this base 10. So this is called the base, and base is 10 in the case of decimal representation. But we can do it with any arbitrarily base b greater than 1. So for example, the same integer can be represented as a sum of powers of 2. So you can see here powers of 2 from 2 to the 0 to 2 to the 8, while this coefficient in front of powers of 2 or either 0 or 1. So you just write a binary string, which is just a concatenation of this coefficient in front of the powers of 2. And you also describe this base you used in this representation. So this is called a binary representation or binary expansion of 351 base 2. And more generally, you can do the same for an arbitrarily base b. So here's a well-known theorem that for any positive integer n and for a base b, so here base b should be larger than 1, there exists unique integer k and unique non-negative integers a0 to ak less than b. So these are elements of 0, 1, b minus 1. And the first leading term is non-zero. So if the leading term is 0, then you can just remove the leading term. So you can assume that this leading term is non-zero. So under these conditions, you can show that there exists one and only representation of n satisfying this equality. So this is called the base b expansion, and you can write ak minus 1, blah, blah, a0 base b. So maybe this is called 비진법 in Korean. So why are we interested in this binary representation or other base representation? So the reason is that on standard computer systems, they are just working on bits rather than digit decimal integers. So many computer systems can run much faster when we implement the algorithm using the language of binary expansions. So each digit, so here digit is called bits in the case of base 2. So when we use a binary expansion, this bits is just 0 or 1. And this is an example of addition circuit between 4-bit integers. So suppose that you have these 4-bit integers. A is 4-bit integers, B is another integers. When you add these two numbers, you can use just the same scribble algorithm for decimal numbers. So you first add this A0 plus A0 and B0, but this integer could be 1, 0, or 2. If this A0 plus B0 is equal to, then we say there's a carry. So this 2 goes to the next bit, 1. So this carry is represented as C1. And we just write XOR here. And the same applies to here. So in the second digit, you have second bit, you have this XOR of C1, A1, B1. And if you have a carry, this carry is sent to the next bit and repeat it until you reaches the nth bit. So this is a very elementary but simplest representation of addition circuit. And in this algorithm, you can easily check that there are big O n operations are required to add two integers of n bits long. So of course, this algorithm is not a very efficient algorithm. So in real computer systems, there's much more. I mean, it's a incredibly optimized algorithm in our computer chips so that it runs really fast. So there are different types of optimizations, like algorithmic approach is just one possible approach, but there are some other approaches like hardware-based optimization, or there are some other memory efficient algorithms, or some other algorithms with minimal depth and so on. So the same applies to this binary multiplication. You must be already familiar with this long multiplication algorithm for integers. You could use the same multiplication algorithm for binary numbers, binary representations. In this case, you multiply this value with 4, 5, 6 respectively, and write the result of this product here. And you perform addition between these three numbers to obtain the final result. The same is done here. So you multiply this number with these 4 digits, 4 bits, and here's the result, and you add these 4 numbers to obtain the final result. And the complexity of this multiplication, Scribble multiplication algorithm is a big O of n squared, where n is the bit length of input data. And again, there exist much better algorithms with different advantages and disadvantages. So some algorithms are So some algorithms are, for example, asymptotically fast. So asymptotically fast means, so maybe you will study these algorithms in later other CS classes, but some popular algorithms are Karachuba algorithm or Tuncook algorithms or FFT-based algorithm. And among them, the most recently developed one came out in 2019, and that has a complexity something like not something that the complexity of that most recent algorithm is n log n, but the previous one there are some other algorithms like n log n, log n. There are many variants based on different approaches. But as you have seen in the case of a matrix multiplication, asymptotically faster algorithms do not always guarantee the faster result in practice when the size of parameters is smaller than some bound. So meaning that this algorithm is of course better than this algorithm in an asymptotic manner, but sometimes some simple algorithms with worse asymptotic complexity shows better concrete performance in practice. So for example, this algorithm of asymptotic with n log n asymptotic complexity is totally useless in practice because this algorithm becomes faster than the previously best known algorithm when n is something like greater than 2 to the 90 or something. So it's faster only when the bit size of the numbers are 2 to the 80 or 90. So that's totally insane. I mean, that cannot be used in practice, of course. We cannot even store such a large number. So instead, but some other algorithms like Karachuba algorithm is widely used in practice. That algorithm is faster than Schoolbook algorithm when the integer size is roughly 100 or 1,000 digits. So some optimized algorithms are really used in practice. So yeah, so if you install some popular high precision arithmetic libraries, they usually provide several options internally. So when you call a multiplication between two integers, they first check the size of integers and then choose the best algorithm known for that size of input. And in fact, this was conjectured in 1971 by I believe Strassen. Strassen claimed that there could be some integer multiplication algorithm over complex n log n, but that conjecture hasn't proved for like almost 50 years, but it was finally recently proved that there exists one, even though it is totally impractical. Okay, and there are some other implications of this binary representation. In cryptography, we sometimes need to compute some values of the form b to the n modulo m for some very large integers b and n. So this b or m could be like hundreds or thousands bits. So log m is like hundreds or thousands. So huge integers. So in this case, how can we compute this b to the n? Of course, the very naive method is just multiply b to an integer one by one. So first we have a b1, which is a b modulo m. b2 is a b times b1 modulo m. b3 is a b times B2 modulo n. Repeat until we obtain Bn. If we use this algorithm, then we can easily prove that Bn is equivalent to B to the n modulo n. So we computed B to the n modulo n. But the problem is that this method requires n multiplication. So the complexity of this algorithm is big O n, integer multiplication modulo n. But the more better option is presented here. So first we compute the binary expansion of this exponent. So here, this 11 is n here. We first compute the binary expansion of this exponent n and use this information to reduce the complexity of this exponentiation computation. So for example, when you compute 3 to the power of 11, the binary expansion of 11 is 1, 0, 1, 1, which is a plus 2 plus 1. So this is 2 to the 2 cubic and 1 and 2, 0. And we represent this 11 as a sum of these different powers of 2. And this is equal to this. And now these three different integers, 3 to the 1, 3 to the 2, 3 to the 4, can be computed very efficiently by repeating squaring of the previous integer. So 3 to the 1 is just a 3. The square of 3 is a square of 3 to the 1. And 3 to the 4th is a square of this square of 3. And 3 to the 4th is a square of this 3 to the 4th. So it just requires only 3 squaring to compute the values powers of 3 modulo 7 values. And then finally, we just need to combine these 3 values to obtain the final result. So what is the total complexity here? So the total complexity depends on the bit size of this exponent 11. So suppose that this is n, then we have roughly log n bits. So the binary expansion of n is a log n bits long. So we have this many powers of 3 here. So we take this log n many squaring operations to generate these values, and then another log n multiplication to multiply these powers of 3. So the total complexity is big of log n, because it requires log n squaring and log n multiplication. So this is a pseudocode, formal description of pseudocode for this modular exponentiation. So you can see that here we represented this exponentiation as a binary representation, and we use this value to obtain this, to compute these powers of b as well as the final result b to the n. Okay. Any questions so far? Great. Okay, then let's go to the next section. So in this section, we'll study primes and greatest common divisors and some other algorithms like Euclidean algorithm. And then in the final subsection, we'll go to the cryptography. So an integer p greater than 1 is called a prime if the only positive factors of p are 1 and p. So there are exactly 2 divisors of p, which are 1 and p. Otherwise, an integer is called a composite number if and only if there exists an integer a such that a divides n and a is between 1 and n. So there are three types of integers, three types of positive integers, 1 and prime, and composite numbers. So any positive integer belongs to exactly one of these subsets, 1 or prime or composite numbers. So 7 is prime, as you know, and 10 is composite number, and 1 is not prime nor composite because it is not greater than 1. So there are three types of integers. And I am also pretty sure that you're very familiar with this prime vectorization. It's also called a 소인수분해, right? Yeah, 소인수분해 in Korean. So fundamental theorem of arithmetic says that there exists a unique representation of prime factorization. So prime factorization basically represents on any integer greater than 1 as a product of powers of primes. So any integer can be represented as like this, where pi's are distinct primes and ei's are exponent greater than 1. This is a fundamental theorem of arithmetic. So we will, I'm not going to prove this theorem right now, but I'll explain the uniqueness of this representation probably today. So, sorry. So suppose that we are given an integer n, and how can we tell if n is a prime number or a composite? So the naive method is described here. So sometimes we want to distinguish if this integer is a prime or not, or sometimes we want to factorize this integer so that we want to find prime factors of this given integer n. So the naive method in the square book method is that just it's called exhaustive search. So just we just try to divide this integer n by integers from 1 to square root to n. So in this theorem, it says that if n is a composite integer, then there exists a prime divisor less than or equal to square root to n. And this can be proven by proof by contradiction very easily. So meaning that if so if n does not have a prime divisor less than or equal to square root to n, then n is a prime number. And so I skip this proof. That's kind of obvious. So when you just want to test if a given integer is a prime or not, what you can do is just to try to divide this integer n by all primes which are not greater than square root of n. And this is called a trial division. So for example, if n is 101, then there are only 4 primes which are less than square root of 101. So you just try to divide this n by 2, 3, 5, and 7, and deduce that this n is not divisible by any of these 4 integers, four primes, so that 101 is a prime. As you probably know, there are infinitely many prime numbers, and you can also easily prove this fact by proof by contradiction. So suppose that there are only finitely many primes instead of infinitely many primes, then we can just imagine the set of all prime numbers, and that would be a finite set because we assume that there are only finitely many primes. And now you consider this integer q, which is defined by product of all primes p1 to pn plus 1. And by the definition, first, this q is greater than this pi. So if this is L, the list of primes, then q is definitely not an element of L because q is not equal to pi for any I. So from the definition of this L, from the assumption, this q should be composite, right? But in the previous lemma, we already showed that from the fundamental theorem of arithmetic, q should have a prime factor. So there exists p prime, so meaning that this p should be an element of L because L is the set of all primes such that p divides q. So this p belongs to this L, so meaning that this p is pj for some j. But the problem is that this is a product of p1 to pn plus 1. So we deduce that pj also divides q minus 1, which is p1 product of p1 to pn, because pj is one of these m primes. So from these two conditions, you obtain that pj divides 1 because from the definition of this division, if p divides a and p divides b, then p divides a minus b. So there was a lemma we showed about this division in earlier slides. So if a and, meaning that if a and b are both multiples of p, then their difference is also multiple of p. So meaning that if q and q minus 1 are both multiple of pj, then 1 is a multiple of pj. That's a contradiction because 1 doesn't have any prime factor. So that's how we show the contradiction and conclude that there are infinitely many primes. So, but the more interesting question is how many primes? I mean, of course, there are infinitely many primes, but the question is how many primes less than a certain bound x? So this is a very popular and interesting mathematical question in analytic number theory or other related domains. So there's a called a prime counting function. This is a prime counting function, which is usually denoted by pi. So the pi of x is defined as the number of prime numbers not greater than, equal to or less than x. And there's a very well-known theorem that it's called the prime number theorem. So pi of x is roughly equal to x over log x, where this log is a natural log. So this roughly equal means this means limit pi of x log x goes to 1. So the ratio between number of primes less than x and the value x over log x, the ratio goes to 1 as x goes to infinity. So this is a prime number theorem. And in fact, this is a prime number theorem, but earlier, back then in 18th century, it was an open problem between mathematicians. So it was back then, it was probably been called prime number conjecture because there was no known proof. So many mathematicians tried to solve it, and and some of them even came up with even improved results recently. So this is kind of the best recent result about the approximation estimation of pi, this prime counting function pi of x. So there's these functions are called logarithmic integral function. The first one takes an integration from 0 to x. The second one starts from 2. So they are almost the same function, but have constant difference. So they have the same scale. So they all have the same scale with x over log x. So this is very the latest proved result. So pi, the error between this pi over x and this logarithmic integral function is bounded by something like this very complicated form. So roughly speaking, you can almost ignore this term. This is relatively minor. So this is again relatively minor. So you have a roughly slightly you have an upper bound which is slightly less than some linear function of x. This is the best known result. And you have heard about, probably heard about Riemann hypothesis. So there are some original form of Riemann hypothesis is about Riemann zeta function, like a root of Riemann zeta function on complex space, blah, blah, blah. But there are several equivalent claims which equivalent to Riemann hypothesis. And one of the equivalent claims can be represented as this prime counting function. So this is open, and this is actually equivalent to Riemann hypothesis. So the claim is that this pi of x is equal to this logarithmic integral function plus this big O of square root of x times log x. So you can see that this is a better approximation than this one, the currently known result, because there's an x here, but this function have a roughly square root of x scale. So you don't have to remember this result, but I just introduced this result for fun. So probably this is the simplest form of mathematical claim, which is equivalent to Riemann hypothesis. So roughly speaking, if you can count the number of primes very well, then you somehow prove the Riemann hypothesis. Okay, so now back to, again, elementary stuff. So I defined the greatest common divisor. So let A and B are integers, both are non-zero, and the greatest common divisor of A and B is the largest integer D, such that D divides both A and B. So the greatest common divisor is denoted by simply GCD of A and B. So it's a 최대 공약수 in Korean. So I believe you're very familiar with this notion. And two integers are called relatively prime or 서로소 in Korean if their GCD is 1. So 17 and 22 are relatively prime because they have a common divisor on just one is just a unique common divisor of 17 and 22. So one is GCD of 17 and 22. And also we define that this sequence of integers a1 to an are pairwise relatively prime if GCD of ai and aj is 1 whenever I and j are different indexes between 1 and n. So just to be careful, this is not the same definition of as GCD So this one and this one are different conditions because so I just defined the GCD for only 2 elements, but more generally, we can define GCD over n integers as a greatest integer d such that d divides ai. So we can define GCD of n integers like this, and and the following two statements are not equivalent. So first, GCD of A1 to AN is 1, and A1 to AN are pairwise relatively prime. These two statements are not equivalent, and you can easily find the counterexample. So like, yeah. Oh, here's actually there's a counterexample here. So these 10, 19, 24 are not pairwise relatively prime because 10 and 24 have a common factor 2, common prime factor 2. But if you compute GCD of 10, 19, 24, then this is 1. Okay, so how can you find the greatest common divisor of two positive integers? And probably in elementary school, we used this method based on prime factorization of the two integers. So when we compute GCD of 120 and 500, we first compute the prime factorizations of 120 and 500. So 120 is a product of 2 3/3, 3, 5, while 500 is a product of 4 and 2 square and 5 cube. So GCD of these two integers are obtained like this. So we just list primes here, and these exponents are taken as a minimum of these two exponents. So more generally, if A and B are two integers with prime factorization like this, then GCD can be computed like this. And LCM, least common multiple, is a 최소 공배수, and you can also compute LCM of three integers using prime factorization. But I just skip this slide because we'll mostly use GCD in this lecture. But okay, so before going to the next section of Euclidean algorithm, let me ask this question for now. So in general, some of you probably know that integer factorization is kind of a difficult problem, especially when the size of an integer is very large. So of course, mathematically, theoretically, we know that there exists unique prime factorization of this given integer n, but in practice, finding such a prime factorization doesn't necessarily have to be easy or easy. So meaning that suppose that n is a p times q, where both p and q are, I would say, 1000 bit prime. So you somehow searched for two 1000 bit primes and just computed their product. So you now have this integer, and you now give this n to your friend and let him or her to find the prime factorization of this n. So if I have only n, then what I can do is, for example, try like try to divide this n by all primes less than square root of n, right? That was called the trial method. So strategy one, like try to divide n by all primes p less than square root of n. So if n is this 1000, if p and q are this 1000 bit primes, then this n is roughly 2000 bit integer. And this is again 1000 bit integer. So we just need to make a list of all primes less than 1000 bits and try to divide n by all such primes less than 1000 bits. And how many primes are there? So we don't know how to prove it, but we studied the prime number theorem. So we know phi of x is roughly x over log x. In this case, square root of n is a 1000 bit integer, meaning that this is 2 to the 1000. So this is 2 to the 1000. To the 1000. So this is not binary log, but the natural logarithm. So it's kind of tricky to compute it. But I would say it's still definitely greater than 2 to the 90, I don't know, 70. So there are this many primes of size less than 1000 bit. And it's physically impossible to just store or find this many primes because of, roughly speaking, 1 gigabyte is 2 to the 33 bits. So if you want to store this many primes, then you need 2 to the 90, 37 gigabytes. It's just physically impossible. So that's why this method is not practical. So multiplying two primes can be done very efficiently using this more long multiplication algorithm. So recall that such an algorithm, the complexity of a long multiplication was n squared. So this multiplication takes only big O over 1000 squared, which is roughly 2 to the 20 multiplication, which is definitely doable because our computer processor can perform like 2 to the 30 several operations in a second. So it's kind of a very easy task, which can be done less than in 1 second. So so the lesson here is that multiplying two integers is very easy, but recovering this factorization form, recovering this prime factor is totally impossible in practice. And it's using this naive approach. Well, of course, there's definitely much better algorithms for factorization, but still it takes much longer. So that's why we don't want to use this prime factorization method in practice, because if n is really large integer, then finding the prime factorization of n takes really long time. So if you use this method to compute GCD of two integers, then you basically need to compute prime factorization of two integers. That's too inefficient. So we want to find a faster method for computing GCD, and that's a Euclidean algorithm. Any question here? Okay. So this Euclidean algorithm is based on just a simple division algorithm we have already seen. So here, as I explained, computing this GCD directly from prime factorization is very inefficient because of prime factorization is very inefficient. So much the inefficient algorithm is called the Euclidean algorithm. So what we are doing here is that when you compute GCD over two integers, I say A, B, you just divide A by B using Euclidean division. So if you divide A by B, then you have a quotient Q and remainder R, right? This R is an integer less than 0 and A. So, or you could say this R is an element of G sub A. So, and there's an interesting property here. GCD of A and B is equal to GCD, GCD of B and R. Oh, sorry, this is not A, this is less than B. So we are dividing A by B, so the remainder is to be less than B. So the reason is that, so if some integer divides both A and B, then it also divides R. Why? Because R is A minus B cubed. So if A and B are both multiples of D, then their linear combination is also multiple of D. That was the property of division. And again, if D is a common divisor of B and R, then this D also divides A. Why? Again, because A is B cubed plus R. So if some integer divides both B and R, it should also divide A. So the conclusion is that GCD over AB was the definition of GCD AB was the greatest integer, greatest common divisor of A and B. But if some integer divides both A and B, then that integer also divides R, meaning that D is a common divisor of B and R. So, and also conversely, if D is a common divisor of B and R, then that D is also divisor of A, meaning that D is a common divisor of A and B. So we proved this both sides of inequality, so that we can conclude that this GCD of A and B and GCD of B and R are the same. And this slide describes just one example of this argument. So A equals B times Q plus R. So computing GCD between A and B is equivalent to computing the GCD of B and R. And one good property about this Euclidean division is that, as you saw, R is less than B. So the size of this input integer is decreasing. So because so when you usually divide A by B, we are implicitly assuming that A is greater than B. Otherwise, there's no point of dividing A by B. So we are having this kind of relation. So instead of computing GCD of large integers A and B, now we are just need to compute the GCD of small integers B and R. So that's probably easier than computing the GCD of large integers. And another good property of the Euclidean algorithm is that it doesn't require prime factorization. So computing this quotient Q and R doesn't require any property of a prime. So you just need to compare the size of A and B and take a quotient of them. So it can be done very efficiently using simple division algorithm, where the complexity is so complexity of division algorithm is a little bit more challenging to analyze because there are some optimized algorithm like based on Newton's method or some others, but that also have some good complexity, much better, and it's much better than prime factorization because that's a polynomial time with respect to the bit size of input. So now we repeat the process. So in the previous slide, we had so we had A, B, Q, R. So instead of computing GCD of these two large integers, now we are interested in GCD of these B and R, small integers. And we repeat process because now this B value goes to A and this R value goes to the position of B. And now we divide this new A by new B and new quotient and new remainder. And if we use the previous lemma again, then the GCD of this 91 and 14 is equal to GCD of this 14 and remainder 7. So we repeat this process. And finally, it is easy to check that this 14 is a multiple of 7. There's no remainder. So GCD of 17 and 7 is exactly 7. So after this chain of GCD, we obtain this final GCD 7. This is Euclidean algorithm. So this is a formal description of Euclidean algorithm. This is a pseudocode. So when computing the GCD of A and B, we first perform the Euclidean division. R is a remainder, which is written as A mod B. And we already showed that GCD of A and B is equal to GCD of B and R. Now we replace the position of so now we can just forget A, but focus on B and R because now we are interested in GCD of B and R. So now we put B value into A and put R value into B and perform another Euclidean division until the remainder becomes 0. So this is a representation based on while loop. This is just a sequential representation describing the process of this Euclidean algorithm. So this is R0 is initial A, this R1 is initial B. So A is divided by B and remainder is R. And this B and R goes to the position of A and B. Perform another Euclidean division. We have another new remainder, and R2 and R3 goes to here and repeat until we have this equation with no remainder. So how can you show that this process terminates in a finite time? So it's easy to show that this process terminates because the size of R decreases after each iteration. So this R2 is a remainder with respect to modulo R1. So R2 should be less than R1. And in the next step, this R3 is a remainder of division with respect to R2. So that this remainder is less than R2. So we have this chain of R values, which is decreasing, but they are all positive integers. So this sequence cannot go forever, but at some point, it should stop. So, so roughly speaking, here you can say this iteration terminates in iteration. So this number of iteration is less than R1 because of there are only R1 integers less than R1. But this is very like a knife and in a loose bound. So in the next slide, we will see some better complex analysis about this Euclidean algorithm. So yeah, and correctness proof is again easy. So this A is R0 and B is R1. And at each line, we can show that GCD of these two values is equal to GCD of these two values, which is this. So we repeat. And finally, R minus 1 is a multiple of Rn. So GCD between R minus 1 and Rn is Rn. So this is a complex, a fine complexity analysis of our Euclidean algorithm. So it shows, it says that if A and B are positive integers, then the number of divisions. So this number of division means this number of iterations in Euclidean algorithm is bounded by 5 times the number of decimal digits in B. That is five times of log 10 B. So I'll prove this theorem in the next class.